Hello, everyone. This is Group 1 presenting digital transmission in free space through a high-powered laser. Our mentors being Dr. Wei and Dr. Carr, our committee being Dr. Sahawin and Dr. Maddox and Dr. Eikenberry. Meet our team. Alexander Simmons, a photonics engineer. Curtis Kane, an electrical engineer. Ivan Huang, a photonics engineer. And Monica Castro-Suarez, a computer engineer.
Sure.
Yep.
All right.
Test
typing.
at 50 feet. Typing.
G R A D U A T I N G.
All right, that's the transmission end. Now walking all the way over here. Just showing one continuous thing. There we are. All right. Testing the input.
All right. Typing nights. K N I G H T.
All right. There's our input nights, and all the way down here. Can you focus this onto here? Now, can you hold this in focus and then type go? Ivan, type go.
Go.
Yep.
G O.
Yeah. Alrighty, there we are.
This is our optical diagram. I will only be going over the transmitter portion of it, which covers the infrared, the red laser beam combiner, the beam expander, the culmination lens, and then the alignment mirrors. The infrared, as you can see, is at 980 nanometers at 600 or 60 milliwatts at higher power. Red lasers 636 nanometers at 5 milliwatts of power. Our beam combiner, then we have our beam expander of 36.1 millimeters and our culmination lens of 50 millimeters. Then onto our alignment. This is the optical layout schematic shown in 3D modeling CAD and what we're planning to print out. Next is it actually being assembled, and you can see our infrared laser, our beam combiner, our red laser, then our beam expander, our culmination lens, our adjustment mirror, and then our output. This is us, or me, testing the system first to make sure for our long distance test that the beam size is what we need it to be. You can see it going through the beam combiner, our beam expander, culmination lens, see there, and then through our adjustment mirror, and then to our output, where you can see it's going and gradually getting bigger. And then for a distance about like 10 to 15 feet, you can see that our beam size is about 1.5 inches. We went later to adjust that. And this is our beam size at longer distance, 60 feet. We did about tested the beam size at about halfway point.
This is the IR.
At a halfway point, you can see us standing there, walking through. So halfway point, about 35 feet. You can see on the IR viewer card right there, about half of it is on the screen. And that's about 1/2 inch to 3/4 inch. And this is the beam size and power test at a distance of 50 feet of our transmission and receiving system. The beam size on the receiving end at about 50 feet was the size of about 1.5 inches by 2 inches, shown on the IR viewing card. And for the power of the laser, showed a max of 2.91 milliwatts using the 60 milliwatt IR laser, and showing the power drop off of the expanded beam on the receiver end. Is our version we had before our final demo at our Creole Showcase project. You can see the version we have showing the character we are transmitting in a loop, the binary code for the character, the modulation board, and the IR laser, transmission, the laser in a loop. And we go through our beam splitter, culmination lens, beam expander, mirror, receiving end, and the receiving end our photodiode, focusing lens. And then you can see at there we have the receiving signal, our high and low signals, our max signal we've gotten through the loop, and the amount of bits that it is read throughout the entire loop.
For the photonic specification, here is a table of values measuring the amount of power captured by the power meter with respect to the distance between the 120 milliwatt infrared laser and the power meter. The relationship is not linear due to misalignment, atmospheric disturbances, beam divergence, and other environmental factors, but the general trend is that most of the power, 80 to 90%, is lost on transmission. However, this is not an issue as the high responsivity of the photodiode and implementation of a transimpedance amplifier will make up for what little power is detected. Another trend is that power loss per feet is gradually decreased, which is a good sign that even at longer distances, the power meter can still detect a fraction of the 120 milliwatt laser as long as the optics of the transmitter are aligned properly. The highlighted values will be later shown in the specification demos. For calculations, the average power detected by the power meter is 10.51 milliwatts, and the average power loss per feet is 2.4 milliwatts per feet. From the average detected laser power, the overall percentage of the power lost is 91.24%, which is to be expected. The expected average photocurrent generated from the photodiode is 6.83 milliamps, which will be amplified with the transimpedance amplifier. The following demos will be shown. As a heads up, a mistake was made in the second demo. I should have said demo 2 instead of demo 3. Demo 1 of the optical setup with the IR laser, the beam expander, and then the collimation lens, and then the focusing lens at a total of 18 feet. The power here is 9.9 milliwatts. Alright, demo 3, same setup, but the distance now is 35 feet, and then the recorded power is about 15 milliwatts. Demo 3, 60 feet away. Recorded power is now 13.6 milliwatts.
This is the start of the hardware design. This slide shows an overview of our hardware pipeline. It starts with a microcontroller that converts written text from the laptop to binary data that will be used to toggle the laser in a subsequent manner so that zeros will represent when it is off and ones will represent when it is on. The laser beam then travels through an optical path composed of lenses and mirrors for beam shaping and collimation. At the receiving end, a photodiode captures the signal and the output current is converted to voltage using a transimpedance amplifier. Using the microcontroller's built-in analog-to-digital converter, the signal is then processed by the microcontroller and its output is then sent to the LCD to be displayed. Using Fusion 360, we developed a detailed 3D CAD model of the physical system, including the PCB container, condensed component layout, and light optical mounting. 2 additional views are zoomed in to show how components like the PCB and photodiode are positioned for alignment. Creating this model helped guide physical prototyping by verifying mechanical fit, optical paths, and wire routing in advance. In this video, you can see our system in action during a test run. The laser transmitter sends binary encoded characters through free space, which are then picked up by the photodiode on the receiver side. Initially, we ran into major timing issues when using an ATmega microcontroller to receive the signal because it couldn't synchronize properly with the MSP430 transmitter, leading to decoding errors. Switching to the MSP430 on the receiver side greatly improved consistency and helped us troubleshoot and verify that each subsystem from the laser modulation to the transimpedance amplifier and LCD output was working as intended. This prototyping stage was key in validating our hardware choices and refining our signal detection pipeline. This clip highlights the receiver side PCB we designed for our optical communication system. You can see the photodiode mounted near the top edge, positioned to capture the incoming laser pulses. The signal then travels through our custom transimpedance amplifier, which converts the light-induced current into a readable voltage. From there, it's fed into the MSP430's microcontroller, which decodes the digital signal and sends it to the LCD. We also included a 3.3 volt and 5 volt regulator for subsystem power isolation, as well as header pins for programming and debugging. Prototyping on this custom board let us validate our design choices in a real-world environment and ensure signal integrity from our optical input all the way to visual display.
Hello, everyone. My name is Monica. This is the test demo that my team and I set up to test for this project, as well as I'll be explaining briefly what the software side of this project is intended to do. This is the transmitter. The transmitter takes the user input from PuTTY via UART and displays it on the LCD. At the same time, it converts each character into 8-bit binary form. For every bit, the user flashes the laser on for 1 and off for 0, holding each state briefly to represent the bit. This way, each character is transmitted as a sequence of light pulses. This is the receiver end. The receiver's job is to detect the laser pulses sent from the transmitter. It uses a photodiode to connect to the ADC pin on the MSP430. As the laser blinks on and off, the receiver samples the light levels and converts it to binary. High signals means on, means 1, and low signals means off, which is 0. After collecting the 8 bits, it reconstructs the original character and displays it on the LCD. This allows the receiver to decode the transmitted message in real time. Thank you for watching, everyone. This is Group 1 with digital transmission in free space through a high-power laser. If you have any questions, please feel free to reach out and let us know. Thank you.